here. I think we've got everybody here. So thanks for coming back, folks. I have homework 4 and grades updated just as of this morning, so you can see where you're at in terms of your current point totals. I know this is the time of year when folks start to get nervous about grades, and so I want to try and keep that current. Everybody's doing fine. So long as you do your work, you will all be just fine. And we still have some stuff outstanding, but everything that you have left to do is available, by the way. So there's 2 formative assessments left, I think. Is that right? Yes, one on Wednesday and then one after Thanksgiving, and 2 homeworks, and they're both up. So you can take a look and see what else is out there. Yes, chocolate frosting on graham crackers. Yes, indeed. It's vanilla, but still equally delicious. I'm not sure there would be a bad combination out there. But with respect to homework 5, let me take a second and pull that up because I want to point out a couple features of the instructions to make sure that you notice that. So 1 second here while I get this up. I should have done so ahead of time, but I was busy thinking about frosting memes. How that happens. So homework 5 is very much a review of the things that we've done in previous homeworks. There's only one new thing that you're responsible for, and I will make sure that we have that covered well this week in classes so that you can be working on that whenever you have time to do so. As a reminder, next week is Thanksgiving week, and so we do not have class. But on Tuesday of Thanksgiving week, I am going to have office hours. So from 12:30 to 4:45 on Tuesday, I'm going to have my Zoom room open and anyone can stop by and talk about anything. And if you don't want to stop by and you want to have a break instead, that is also very fine with me. So homework 5, let me pull this up here. So this is a story about predicting first-year ratings of graduate school performance from your enthusiasm for completing regular graduate school tasks. So there's a scale of 1 to 7. And GRE scores, this is archival data, so they're on the old 500 scale, a 500 mean scale, 200 to 400, 200 to 800, as well as a three category variable, which is fear of statistics. So low, moderate, and severe. So the variables in question, you'll need to make a centered version of enthusiasm, and you'll need to create centered versions of the other predictors. You know how to do that. Let me find the part where it says it centers. Here it is. Okay, so this part of the instructions right here. For your predictors, center motivation at 4, center verbal GRE score at 500, and center quantitative GRE at 550. For the coding of fear of statistics, so the original variable that has 3 categories needs to be converted into 2 dummy-coded predictors with low as the reference group or little as the reference group, and one of the predictors is supposed to represent little versus moderate, and the other is supposed to be moderate versus severe. So this is a slightly different coding scheme than what you had to do for the golf thing, but as a reminder of what that would look like, if you revisit the coding for the happiness ordinal predictor in example 4, that will give you a template for what this is going to look like. Other things that I want to point out in terms of the instructions, note there are 2 troubleshooting steps to complete for each model. Each model is going to ask you for the residual variance to start with. If you don't have the residual variance correct, then you do not have the right model contents. Either your outcome variable is wrong or your predictors are wrong. But if you do have the residual variance right, then at least you have the right configuration. The next thing is going to be the fixed intercept. And the reason I ask for that is to check your centering. So if you have the residual variance correct, but your fixed intercept estimate or standard error is incorrect, that means the predictors that are in the model have not been centered with the right constants. So those are two things that you can check to make sure that you've got the right model. So this series of questions starts with an empty model. So just to review, what's in an empty model? This can be a gesture one. Zero predictors. Yeah, just the intercept. So the empty model residual variance represents all of the variance that there is to be had. So that's a baseline for judging improvements to the model. Then I'm asking you to add in a linear effect of motivation and to report on the proportion of variance accounted for by the model. What is that called on your output? Proportion of variance accounted for is otherwise known as what?
R-squared?
We have a vote for MSE. MSE is residual variance. R square is what the proportion of variance accounted for is. So if I start with an empty model and I add in one predictor, that the R square for the model tells me how much it's increased relative to 0, which is what it would be in the empty model. Then I'm asking you to add in 2 new predictors to that model. So leaving what you have and adding things to it. So the sequence is different than what it was in homework 4, where I had you test one set of predictors, take them out, and then test a different set. This is a building kind of exercise. So you would be adding linear effects of each of the GRE scores in this, and the model is still going to give you the R square directly on your output for how much variance has now been accounted for. But I am also going to ask you for the change in the proportion of variance. And as it says in the instructions at the top, that you are going to have to calculate manually. So one of the very few things this semester that I want you to get your calculator out for. So you have the R square from the previous model, the R square for the current model, and question 20 here that I have highlighted, for instance, is asking for the difference. It's just a simple subtraction. You can make Stata do it for you. If you type display and then write out what you would type into a calculator, the answer will come back in your output. So you don't even have to get a separate calculator out. You can do that in SAS too if you put it in a data set and print the data set, but calculator is probably more straightforward. So this is not something that you have to ask the code for. It's something that you have to find by comparing the two sets of outputs and looking at the difference in the R square value that was provided by each model. The new thing, the thing you haven't been asked to do yet, is right here, an example of it. A test statistic for the change in the proportion of variance accounted for. That's the one new thing that's in this homework. So the idea is, if I've added 2 new slopes to the model, those 2 new slopes hopefully have increased the R square. I can calculate the increase in the R square, but I need a significance test to go with that. So to be able to lump the new slopes together to get a joint test of their significance, that's the new thing I'm asking for in this homework. Everything else you've done before. So any questions on any of that? And this is what we're going to go over today. Yep. Okay. Then let us review. Who wants to look at PowerPoint? Not me. Let's look at the beach. There we go. That's a better background to review with. So what have we been talking about? This is us. Touche. Yes, this is us as my metaphor for partitioning variance. Unique contribution, multiple predictors. Yes. GLM with multiple fixed effects and multiple predictors at the same time. Yes, that's what we've been talking about. So the idea of being able to examine the effect of a predictor in predicting an outcome and to see whether or not that predictor's effect is usurped by other predictors. The extent to which a predictor still matters, so to speak, after controlling for other variables that are also related. So being able to take the total prediction of an outcome and carve it up into pieces. How much is due to this predictor, how much is due to that predictor, and how much is due in common that still counts towards R square, but doesn't count towards any of the predictors. That's what we've been talking about. And being able to add sets of predictors to models and to get the unique contribution of each set of predictors with an F-test and a change in R square. All right, let's take a look then at example 5A. We started looking at this before. We have this one to do, and then I made another example that's actually more of a review activity. So we'll see how much time is left today, whether or not we start that or whether we start that on Thursday. So example 5A is featuring the same data that we've been playing with all semester, predicting annual income. And this is building on the results of example 4, where we had a 3-group variable for working class status as one conceptual predictor. The 3 groups took 2 slopes, though, to be able to distinguish the 3-group means. We had age, and we had linear and quadratic slopes for the effect of age, so 2 slopes to be able to describe the effect of age. And then we had education, which I had carved up into 3 sections of education, 3 subsamples, so to speak, before high school, people who graduated high school, and then after high school. So in example 4, we had looked at the effect of each of these predictors separately, and we had determined how much variance each construct as a predictor, working class rating, age, or education accounted for. So in this example, what I want to do is put them all in the same model at the same time to see to what extent each of their effects still holds after controlling for the other things. So to what extent does age still matter after controlling for education and working class? To what extent does education still matter, and to what extent does working class still matter? That's the idea here. In research, the order in which you would put predictor variables into a model is going to be guided by your research questions. So in this example, if I were doing this, say, in a real paper, and I needed to control for age, let's say that's one thing that people just want me to control for. Someone else has shown that age is related to my outcome of interest, and so I need to address that before talking about novel contributions. Age would go in first. I'd probably have a model with just age in it. I'd talk about the effect of age, and then I would add things that I'm focusing on. To what extent does this new thing that I care about improve the prediction of the outcome above and beyond age? And I would talk about it from that language. If instead education was the control variable that someone else cares about that I have to put in, I would start with education in the model, talk about that, and then add the other predictors that I care about. So there's not necessarily a right or wrong order to putting these things in the model. Once they're all in the model, the results are exactly the same as if you had started from a different place. So when they're all together, the way that we evaluate these things puts them all sort of on the same playing field. They're not hierarchical, so to speak. There are versions of these statistics that are hierarchical, and they're not usually appropriate, which is why we're not covering them. That's going to be something called type 1 sums of squares, whereas what we have is known as type 3. So there is to say there's an art and a science behind building models. You're trying to answer research questions and let your results tell the story of your data in response to those questions. But if you start from a different point with respect to your questions, that's going to lead you down a different possible sequence of models. So I just want you to have the tools to be able to phrase these however you think is most appropriate for you, and then to be able to judge how your predictors improve the model, no matter which way you want to put them in. So does that make sense? Maybe? Okay. So we have then, first step, always import your data. Data transformations. So this is an example of a 3-group coding scheme where I have determined the first group is going to be my reference. And how do I know that just from looking at this code that that working class equals 1 is going to be my reference group? Yeah, zeros. That's where they're both 0. Now, I will tell you that this coding scheme is very close, but not exactly what you need for homework 5. This coding scheme gives you group 1 versus 2 and group 1 versus 3. What I asked for in homework 5 is group 1 versus 2, but group 2 versus 3 is the second contrast. So I will let you try to figure out how to change it to make that interpretation correct. But if you stick with it this way, the answers to some of the questions are going to need to be found as linear combinations, whereas if you code it the way I intended, they will not. So not very many, if any, lincoms or estimate statements required in homework 5.
I'm sorry, Lisa, could you, just quick question.
Sure.
For those 3 groups, 1 is the reference group, 2, excuse me, is group 1 versus 2, and then that third group is 2 versus 3?
That's what I want you to do. That's not what this does.
Oh, okay.
This does 1 versus 3 as the second variable that's being created rather than 2 versus 3.
So we want 2 versus 3.
You want 2 versus 3.
But we're actually going to have 1 versus 2, 2 versus 3, and 1 versus 3.
1 versus 3 would be the linear combination found with the other 2.
Ah, sure.
So you only need 2 contrasts. The third can always be found as a linear combination.
Okay.
Thanks for the question.
Okay, thank you.
Sure. So you'll have to do this for the fear of statistics variable. Centering a regular predictor. Just to remind you how the code works here, it's the new variable to the left-hand side of the equals, so you come up with a new name. It should be a different name than any variable that currently exists in the data set. Stata, I think, insists you do that. SAS does not. So you can accidentally write over your data in SAS, which means you'd have to re-import everything from the beginning. But it's a function of the old variable and then the centering constant. So if you're centering at 18, then you would subtract 18. If you're centering at 30, for instance, you'd subtract 30. And then piecewise coding, which is shown here, you guys don't have to do any more. We're done with piecewise. Hello. Yes. Hands up top. Unless you come back to the longitudinal class in the spring, in which case, yeah, you get to do this again, but you'll already know it. Whereas some of your classmates will not have seen this before. So you get the advantage on that one, but no more piecewise models. But the idea.
Quick question, Lisa.
Sure.
So for centering, I know that in the homework we were going to center a few different things. I can't remember all of them now. Can we do that all in one area, or do we have to separate it out?
Great question. You can choose to do it either way. Strategically, I think it makes sense to do it all in one area, because that way all of the steps you need to prepare your data set for an analysis are done in one place, and you just run that code and you know it's ready. If you split it out the way that I had been doing in the handouts, then you have to like stop and run separate chunks, and it's easy to miss one when you try to go back to where you were. So I had initially set up my handouts to look like this, where it's all done in one place, but then people got confused because then they didn't understand how what happened on page 1 wasn't needed until page 10, right? So I split them up in the way that I had to make that point. But yes, in life and in this handout, for instance, I'm doing them all in one step. All right, other questions? Thanks for the questions, guys. I appreciate it. All right, so making new variables here, make blank versions, and then filling them in with conditional logic. So this is creating the 3 piecewise slopes that we've had so far. And then selecting complete cases. This is not something you need to worry about in your homework, but it is something that you would need to worry about in life, which is why I'm putting it here. By the way, if you are finding yourself down the road having to do analyses that I don't have an example for in this class, please let me know. I'm happy to find another example or to help you conceptualize your problem. This is not an exhaustive list of every type of model setup you'd want to have, but I have taught a lot of classes. So odds are good I have some kind of example that would fit closer to what you need than what's here if I don't have anything. So please let me help you if I can. All right, Stata folks, your process looks very much the same, except for the word gen. Gen stands for generate. That is what you need to create new variables. And then the replace changes the zeros and ones given the conditional logic of which group they're in. And centering looks like this. It's the same except for no semicolons. And then again, conditional logic for the pieces. Okay, and then we looked at this last time. Here's our model. So what this model is saying in English is that income for each person, so that's my Y sub I, is going to be a function of this thing. What's that? I don't know if you can do this with hand signals, but I'll take chat window or voices, your choice. What's Beta0? Intercept, yes. What's the definition of Beta0?
No predictors.
Close. Reference point, I will take that. It's the intercept when centered at 0. Getting there. So Beta0 is what Y is predicted to be when what is true? All the predictors are 0, yes. So the analogy I use for this is the "you are here" sign of the model. It's your reference point because Y is expected to be the intercept when all of these other terms zero out. And if these terms weren't here, then Beta0 would just be the sample mean. So a lot of different words are used for the idea of what Y is predicted to be. You may hear expected value, conditional mean, Y hat, predicted outcome. Any of those things refer to the idea that this model is using this predictive information to build a predicted outcome for each person. So inside here, I've used color to help offset these things. All of these betas more generally are known as fixed effects. Fixed effects come in 2 flavors. They're either intercepts or they're slopes. This one is an intercept. The rest of them are slopes. Why don't the beta 1, 2, 3, etc. slopes have an I subscript? So the red terms, the fixed effects, fixed intercepts and slopes, they don't have I's. Why is that? Yeah, they're constants. So terms in this equation that have an I are variables. They're things that vary across people and what their values are. Terms that do not have an I are constants in that they do not vary across people. So everybody gets the same Beta0 applied to their score. The effect of low versus middle, for instance here, beta 1 is the same beta 1 for everybody. We don't know what they're going to be yet. That's the job of the software to crunch the numbers and to tell us, but they're constants. Do you guys know how to write equations in Word, for instance? No? Would you like to learn? Can I do a quick demo? Because it looks nice in publications if you can provide a model equation. If not inside the paper, but inside an appendix. One of the tricks it's not really a trick, but it's a good thing in from many perspectives. If you can clearly convey what your model says, and if you can put, say, syntax in an appendix, like literally the code that you use to fit it, that will help make people understand exactly what you did, and it may help other people cite your paper who wouldn't otherwise because they were following what you did. So being transparent can help in a lot of respects. Here's how we write equations. The long way behind writing equations, let me move this thing here, is to go up to Insert, and then there's Equation Editor somewhere up here, and it takes forever. Keyboard shortcut to typing equations is Alt and the equal sign. If you hit that, a little box pops up that says Type Equation here. Now, once you're inside the equation, of course it takes longer because I'm doing all of this stuff, there is an equation menu that has all of the special characters and whatnot, but it's actually way faster if you can use shortcuts. Way faster, meaning it goes faster, assuming that, there we go. Now I've got it. Now watch what happens. If I do a slash and then the word beta, I'm going to hit the space bar and it jumps into a beta. So you don't have to go hunt and peck for all the symbols. This works for any Greek letter. Another one that I sometimes do is gamma in my other class. I'll pop that in there. Sigma. So you hit the slash that is above the enter key and then the name of the letter, and you hit space and it jumps to become a Greek letter. Subscripts. So once you're next to your beta, for instance, if you hit underscore and then the value that you want the subscript for, and then hit space, it becomes a subscript. So this is partially, I think, why people say things like beta sub 0 for like subscript, is because I'm literally thinking like in terms of what I would type to make it. If you need to do superscripts, so for instance, sigma squared, that is a caret, the thing above the 6, and then if you hit the spacebar, it jumps up. You can also do a combination of subscripts and superscripts at the same time. If you were to then do sub E, then it understands you're trying to do that. What's that, by the way? Sigma squared sub E has a special name. MSE, residual variance, yes. That's the symbol for it. So by using the equation editor, you can write out the model and it will look nice like this.
Lisa?
Yeah.
You have a resource that you use to learn all of these shortcuts, or have you just picked them up over time?
Pick them up over time.
Okay.
There's also, I have a program called MathType that is like an equation editor that is, so previous versions of Word were really crappy with equations. And starting in, I think, maybe 2010 or so, it was actually a decent version. And so MathType is a program that older journals and things that, that still use older versions of Word may require that too. I would ask the Google, keyboard shortcuts for equations. This also works, by the way, if you know the program LaTeX. People who do scientific writing often write in LaTeX, and these same commands can be used in LaTeX. I think that's where they came from. So I've just picked it up over time. The one thing that I don't know how to do with a keyboard shortcut is to put a hat on it. So if I wanted to have like a Y hat, so whenever I would need to do a hat, I go up to the design menu, and then there's an accent thing, a menu that has dots, hats, bars, and so forth. So you can see all the different choices as it starts to fill in here. So if you can't find something with menus allow you to fill in all different aspects of equations. I just learned the type, the letter thing from LaTeX. So a W, a Mac, and Control equal opens the equation editor. Yep. So it's Alt equals, and it's probably something, yeah, the Control versus equals on a Mac. So pretty cool, huh? Yeah, it's much faster than doing the hunt and peck for insert symbol and then finding all of that stuff. So cool. All right, other questions on equations, stuff like that? I used to be somebody who would gloss over subscripts, be like, do you really need all these little I's on here? Like, and some textbooks don't use them at all, but the further you get along in statistics, the more important you realize it is to clarify what terms vary over what and which ones don't. So any term that is a variable that varies over a person gets a sub I, and any term that is a constant does not. All right. So let's take a look at what it looks like to put all this stuff together. So I've got the SAS version and I've got the Stata version as well. So with respect to putting all of these terms in the model simultaneously, there's nothing different. I have returned the options, so the slash and then these things control what output gets shown to the second line. So there's only one semicolon at the end of the whole thing, but otherwise it's exactly the same. So the outcome variable goes first. Think of it as the equation. It's to the left of the equal sign. And all the terms that get predictors are on the right. So how many terms do I have listed here? 1, 2, 3, 4, 5, 6, 7. So I'm asking for 7 slopes simultaneously. There's one more term that I'm asking for, but I don't have to write it, and that's the fixed intercept. The fixed intercept is always there, so you don't have to refer to it in the code. So here's the missing group difference that is implied by the model. So the model is automatically going to give me low versus middle and low versus upper. It's middle versus upper is the one that's missing. And so this contrast is going to get me, or excuse me, this estimate statement is going to get me that. So if I want middle versus upper, then the variable that has middle in it gets the -1, and the variable that has upper in it gets the 1. If you were to switch these numbers around, you would get the same numeric value, but its sign would be opposite. So you'd get the difference of how middle is relative to upper rather than how upper is relative to middle. So the p-value would be the same though, and the inference would be the same. It's just from a different direction. Okay, the new stuff, the new thing on homework 5, how you test whether or not things that have been added to a model result in a significant increase in R-square. That's what we're looking at right here. In SAS, it's known as a contrast statement. Contrast statements more generally allow you to lump effects together to get a joint test of those lumps. So we're asking for F test statistics for the joint test of multiple slopes at the same time. And the lumping, as we talked about it last week, how you lump things together is up to you. I'm showing you several different examples of when you might want to do this lumping. One that we have been using so far, but we haven't talked about it that way, is given by the first instance right here. This contrast statement has every single slope that's in the model included with a 1 after it. It just means that we want one of those slopes. Commas are important. The commas delineate numerator degrees of freedom. So how many slopes are being tested? So if you forget your commas, it won't understand that you're trying to lump together separate slopes, and it will try to create some kind of new slope that's a linear combination. So commas are important here. So the F test for the model, the thing that has been given to us by default this whole time, this is how I would ask for it. This is just an example. You don't have to type this because GLM gives you the test of the model, whether all of the model slopes work together to significantly predict outcome variance. It's also a test of the model R-square. Each of these others is a subset of just the slopes that I want to lump together for that purpose. So for instance, why would I want to lump those two slopes together? Those are the two slopes that work together to give me my three group means for the three group variable. So lumping them together gives me what's known as an omnibus test. This is a ANOVA language as to whether or not there is a group difference due to working class across the three groups. So lumping those two slopes back together again gives me a joint test that I can say, does working class rating matter? And if the F test is significant, I can say, yes, it does, and then dive into more specifically which groups are different than which other groups. Likewise, you can think of this contrast with age and age squared as referring to the Omnibus Effect of Age. To describe how age predicts income requires two slopes. They work together. So I want a joint test of the contribution to the model of age. So I'll get an F test and I'll get a effect size for that. And then likewise, a lumping of the three education slopes. So I can ask, does education matter? Get an F test that answers that question and an effect size that answers that question as well. And this, by the way, is me saving output to compute effect sizes for each of the slopes. You do not need to do that, but I wanted to show you how in case you would like to learn how to do that at some point. Okay, how are we doing with the lumping? Okay, so if I had a series of models, for instance, like cough, cough, homework 5, and I had you add, say, 2 new slopes to the model, I would write one of these statements that have those 2 new slopes on them. And that contrast would give me the F test for the change in the model after adding those 2 new slopes and the effect size that goes with it. I don't believe I asked for semi-partial correlations in homework 5, just the change in the R-square, because Stata and SAS do those things differently. Okay, questions, comments?
So for the lumping,
Mhm.
you mentioned that the L versus M and the L versus U will give you all three groupings together.
Yes.
So is that going to be, when we do this for our homework, it's going to give us all 7 groups together?
In this case, we don't have 7 groups.
We have 7 slopes.
7 slopes to describe 3 different variables. So one of the variables is a 3-category grouping variable of low, middle, upper. One of the variables is age, and it has a linear and a quadratic squared slope that goes with it. And the third variable is education, which has 3 slopes that go with it.
Okay, so that makes more sense. Okay, thank you.
Yeah, so we're mixing and matching, by the way, categorical predictors and quantitative predictors. So this is officially either an ANCOVA or a multiple linear regression. Take your pick. Do you want to see the output first, or do you want to see Stata code that goes with the same idea first? What would be more useful?
Stata, please.
Stata, please. Since you said please. Skipping ahead, here we go. I'm on page 5. So the same model, the command is still regress. Income is the outcome variable that you have to have first. Here's my list of 7 slopes. So C dot in front of them to make Stata do math on them later. We have our friend the pound sign or hashtag that defines the interaction term in Stata. Here's a lincom that gets us the third group difference that's implied by the model. So again, the term that has the middle in it, by giving it the -1, we're setting that up as the reference of the comparison, and then upper gets the 1, so it's going to translate as to how upper differs from middle as the group comparison. The analog to contrast in Stata is called test. And so the way that these codes work is that in parentheses is one slope, and you're setting it equal to 0 as what you're actually testing. So that's implicit in the SAS code, it's explicit in the Stata code. So each parenthesis set represents a numerator degree of freedom. So what SAS does via commas to delineate degrees of freedom, Stata does via parentheses. And this thing out here, the 3 slashes, that is a line continuer. Because if your syntax in Stata spans more than one line, you have to tell it to keep reading. Otherwise, it assumes when it hits the end of the line that it's done. Someone told me the latest version of Stata has done away with this, but I want to keep all of my code backwards compatible, so I'm keeping it in. So these 2 lines are one idea, one test statement. And I'm using comments to correspond to the labels that I had in the contrast statements in SAS. So SAS insists that you label your output as to what you're asking for, and Stata does not. But I still think the labels are helpful. That way they echo back in your output window and you can see what you've asked for. So when I'm writing all 7 slopes in one test statement, what I'm asking for is the f-test for the model. I don't have to write that, it's already given to me by default, but I wanted to show you how one would get that. Likewise, the f-test that corresponds to the Omnibus effective group, I would get by lumping those 2 slopes together that correspond to low versus middle and low versus upper. The f-test for the Omnibus overall effect of age, I get by lumping the linear and quadratic age slopes together, and then the Omnibus effect of education. So for whatever reason, people say omnibus instead of overall, but you can think of them as synonyms. So joint, omnibus, and overall all are conveying the same idea, that it takes multiple slopes to describe the effect of one variable in this case. So that's why I've lumped them together in the ways that I have. Okay, Stata folks, questions on the code for this? So again, this is the one new idea in your homework. The idea that as you add things to the model, that you can ask for a specific test of just the slopes you added. Okay, I'm going to show you Stata first because the output for SAS is more in depth. Stata unfortunately does not provide effect sizes that go with these tests. I will show you how to do that to reverse engineer it, but it takes some actual arithmetic, unfortunately. So here is the results for the model. What's that right there? MS residual, otherwise known as residual variance, yeah, sigma squared E. So that's variance left over. That gets reported as part of your results. And I always start with it in homework because if you get this right, that means you have the right contents of your model. So this number, this 136, represents the amount of variability in income that is left over. So the idea of residual means what we don't know yet. This is all of the variance in income that is unexplained by the model, that is left over. The complement of that number is given by R square. So what R square tells us is how much of the variance we did explain. So if I have an empty model with no predictors in it, R square is going to be 0. As I add predictors, hopefully I am explaining variability. R square should be increasing because R square tells you what you got, and that corresponds to a decrease in residual variance. So variance should be going down, which means R square is going up. So these two numbers are telling you about the same phenomenon from a different perspective. Residual variance tells you how much is still out there to be explained. R square tells you how much you've got so far. So another way of saying this is, let's see, this is about 29%. So doing math in my head, that is going to be 61. Did I get that right? 71. 71, yeah, I was overcompensating. So if my R square is 0.29, if I got 29%, that means 71% is still out there. So this number over here, this residual variance, that's 71% of what was originally there. So if I ran an empty model, if I remember correctly, the empty model residual variance was about 190. 71% of that variance is still there, which is 136. 29% of it we have accounted for. So the 7 slopes as a whole have accounted for 29% of the variance. Is that good? Do I have, say, a test statistic that would comment on whether 29 is good? Yeah, it's just right above here. So in Stata output, it's given to you right above this F test right here. So that is the joint test of all 7 slopes that we put in the model being different than 0 simultaneously. F is a ratio of information captured over information outstanding. So 42 on 7 degrees of freedom for the numerator and 726 degrees of freedom for the denominator, which is based on sample size, gives me a p-value that's 0 to 4 decimal places. So this F is significant, unlikely to be obtained from a distribution where the null hypothesis is true. If the null hypothesis of 0 slopes were true, we'd get a result this strong less than 0.01% of the time. This number right here, you can think of the 726 as how many more slopes I could have added. I have 734 people in this example. I have fit 1 fixed effect for the intercept and 7 fixed slopes. That gives me 726 left over. All right, how are we doing so far? Okay, so what this table tells me right here is that I have a model that works. The income level that is predicted by this model is significantly correlated with the real income that we have measured in the data. The square of that correlation between model predicted income and real income, the square of that correlation is my R square. So that's another way of thinking about R square. You can think about it as the proportion of variability in the outcome that the model has captured, or you can think of it as the square of the correlation between the predicted outcome variable and the real one. Either way. Now, do I know if Do I know anything about my individual predictors just from staring at this table? I don't know anything yet. So this is like a general sort of big picture overview. I have to dive into the results more specifically to get a sense of how each predictor fared. So in this model, what's that thing? Stata folks are used to looking at this. What's that? That's what Stata calls the intercept. It calls it the constant, which I hate that language because all of the fixed effects are constants. But this is the constant as opposed to the constant slopes. So this number right here, when I saw this, I was like, okay, this is an unintended demonstration of collinearity among predictors. -3 is my constant. So the model is telling me that somebody who is at the reference point for the model is expected to make negative $3,000 a year. Now, what kind of person is that? Let's go through the list. What is the intercept conditional on? Well, somebody who's in the low group, because based on the first two rows here, that's when those predictors are zeroed out, is when you're in the low group. Somebody who is age 18, so they've self-rated themselves as being lower class, they're an 18-year-old, and I have to go back to my coding to figure out when these three predictors are zeroed out, but it happens for somebody with an 11th grade education. So for that combination of predictors, the model says they're supposed to make negative $3,000. There may not be anybody in the data set who meets all three of those. But that's the reference point for the model. So relative to somebody who makes, relative to somebody in the low group, somebody who rates themselves as being middle class is expected to have what kind of income? First choice, higher or lower? Higher, and I know that because the coefficient's positive. So relative to the low group, the middle group is higher because this coefficient is positive. Is it significantly higher? And I know that based on my handy dandy P column. So just to remind you how I got over to P, if I take the coefficient and divide by the standard error, one more time with feeling, what's a standard error?
The sample's distance from the population parameter.
On average. Yep. So the meme that I showed at the beginning of class of expected value versus variance, that works here too. Because you can think of this slope as an expected value for what the effect of this group difference is. But if I were to redo the study over and over and over again, I would expect it to be off from whatever the true value is by this much. The standard error gives me the inconsistency of this size of effect across samples. So if I take my coefficient, divide by my standard error, that gives me this T column. So in your results for publication, you do not need to give T. If you give your readers the coefficient and you give them the standard error, they can compute T. And the only purpose that T serves really is to get the p-value that goes with it. So the three columns that you would need to report is coefficient, standard error, and p-value. Some people shortcut the p-value column by putting stars in. If you're going to do that, by the way, you got to get off the fence. So you will see this all too common where it's like 1 star for p less than 0.05 and 2 stars for p less than 0.01. But that's cheating. You're supposed to pick an alpha and stick with it. So the star thing, that drives me nuts. I often don't like to spend the space to put the stars in because it makes your numbers look a little wonky sometimes. I've started bolding things that are significant. Certain journals will allow that to happen. I think it makes it a lot clearer for a presentation. Just put it in a table note that bold text is used to indicate results that are significant at p less than whatever your alpha level was. Likewise, these last two columns, these are your confidence interval. This is the interval in which 95% of repeated samples would contain the true value. I don't personally find these very helpful, but some journals want them, which is why I wanted you to know how to get them out of your software. But once again, this is a linear combination of these two numbers. So if you take your point estimate, the coefficient, critical t-value times standard error is what makes that confidence interval. So if people know what your sample size is, they know what your critical t was. If you give them the coefficient and the standard error, they could make their own confidence intervals at whatever level they wanted to. So that's not strictly necessary to be given also, but a lot of journals want them. But standard error is one thing that people sometimes forget, and it's imperative to report it because this helps readers understand how precise of a measure of this slope you actually have. So coefficient and standard error, that's what goes into your report at a minimum. Likewise, low versus upper is given by this one. So I know that the upper group is higher by 7 relative to the low group. Now if I look at these two numbers, do I know how different middle and upper are based on these two numbers? Could I get my calculator out and figure it out? Sure. It looks like the upper group is different by 1.2. That's the difference in my slopes. And several of you, I think, figured out that you could shortcut your estimate statements by getting your calculator out and calculating the difference of your slopes or your groups. But what we can't shortcut is the standard error that goes with it. So anytime that you have a linear combination of fixed effects that creates some other quantity, there's a standard error that goes with it. And that standard error is also a linear combination that takes into account these things as well as their covariance. So the nice thing about the lincoms and the estimates is that it does all of that extra math for you to get the standard error. And so getting that 1.2 as the test of the difference between middle and upper was the purpose of the lincom that's shown here. So 1.1 with the rounding, and it's not significant. So then the story is middle and upper are still significantly higher than low after controlling for age and education, but middle and upper are not different still. Likewise, if we go through age, so this linear slope at age 18, this coefficient of 1.07, that is specific to age 18 because of the quadratic term that's in the model. So at age 18, for every additional year older you are, for a 1 unit change in X, predicted income goes up by $1,000. That's what 1 means. But the quadratic slope is going to modify it. So there's 4 possible combinations. I want you to pick out which one this is. The quadratic slope can take a positive linear slope and make it more positive or less positive, and it can also take a negative linear slope and make it more negative or less negative. So if we start with this slope is positive. Does the quadratic slope make it more positive as age increases or less positive? More for up, less for down. Down, yeah, this is a less positive. This is creating a U shape that goes like this, where the effect of age is slowing down, is decelerating. And the way that we talk about this coefficient is that we have to multiply it by 2. Twice the quadratic is how the linear slope changes. So I would say that the effect of age becomes less positive by twice this number for every additional year of age. And those are both significant. Okay, how we doing? All right. And then these three, these are all linear slopes, but they apply to different regions of education. So for people who have less than 11 years of education, for every additional year that they have, income is predicted to go up by 0.25, so about $260 non-significantly. The boost for graduating high school, which is what this variable represents, going from 11th grade to 12th grade, is about $3,000, which is no longer significant. It used to be, but this p-value would not be considered significant if we had our alpha at 0.05. And this is exactly the kind of result, though, that if you read about it in a paper, people start coming up with euphemisms. So this is trending towards significance. It's marginally significant, it's borderline significant, and my personal favorite, it's approaching significance, which means if you leave your computer running and come back in a few hours, it'll be significant. Just wait. It's approaching. I once went to, I heard a talk by Don Hedeker, and he made a joke that what if it's not approaching significance? What if it's running away? Like if you come back later and it's even more non-significant, that could happen. But yeah, some sort of euphemism for, I want to talk about it even though I know it's not significant. And the last one, for every year over grade 12, you get another $1,500, and that's significant. So each of these coefficients tells us what the effect is of that variable after controlling for each of the others. So it's what does education contribute that age and working class do not? What does working class contribute that age and education do not? That additional layer of interpretation is referring to unique effects after controlling for the other stuff in the model. But what we don't yet know are the significance tests and effect sizes for each of these variables as a set. And that's what the test statements are going to tell us. So here's the first one that I said you didn't have to write because it's just reproducing the model f-test. So if I test all 7 slopes simultaneously, that's the same thing as giving me the f-test for the model. So that's the 42 that was at the top of our output that we didn't have to ask for. Here's the lump, the test statement that corresponds to the 2 working class slopes that work together to create the 3 group differences. They have an F of 21. Here is the lump of age, linear and quadratic slopes put together. They have an F of 41. And then the 3 high school slopes lumped together gives me an F of 27.46. So I have a significance test, but I don't have a ready effect size that goes with these. That's something that Stata does not provide directly. However, if you enter the terms into the model in a stepwise fashion, then you can get what the R-square is at each stage and calculate the differences in R-square to go with these things. And that's what I'm asking you to do in homework. So you start with an empty model, add in enthusiasm, check the change in R-square, add in the 2 GRE effects, check the change in R-square, add in the grouping variable for fear of statistics, check the change in R-square. So that way you can get your effect sizes as change in R-square. That's known as hierarchical or stepwise regression. Okay, so questions on the Stata output so far?
When the lumping comes back as significant, that means that it's adding something to the model, correct?
Mm-hmm.
Okay.
Yep. So to find out the effect size for what it's adding is the tricky part. In Stata, you have to do it either by running separate models with only certain things in them, or basically that's the same premise of what follows here. To be able to calculate the amount of the amount of the R-square that is due to a particular predictor, which is the semi-partial correlation squared, as the effect size that goes with it. And so the rest of this is showing you how to generate that additional output, but I'm not asking for you to do this on your homework. So when
Lisa, I also had,
yeah, go ahead.
the stepwise regression that you were talking about with Stata,
Mhm.
is that what's pictured right where you are right now?
Sort of.
Okay.
So
We would just take words.
So in this case, yeah, what I'm going to show is how to compute the amount of the R-square that is due to a particular set of slopes. So the term for this is the semi-partial correlation squared. It's what's known as eta square on output in SAS, but more generally it is the amount of the R-square for the model that is due to that set of slopes. SAS gives this to you as part of your output, but Stata does not. So to get it out of Stata, you have to fit a model that does not have those terms that you're asking for the effect size for to see how much of the R-square would have already been there, and then you can get the difference. So the formula for semi-partial R-square is the sums of squares from the full model minus the sums of squares from the model without the terms that you're testing, divided by the sums of squares for the full model, for the total, excuse me, which is overall. So let me show you where these numbers came from. So if I go back to my main model here, sums of squares column is what I'm pulling from. Here's total. So that is the numerator of the variance equation for my outcome variable. That's all of the information that there is in income. The full model that has all 7 slopes got this much. So the question is, of this much that's due to the 7 slopes, what part of that was due to, say, these 2 slopes for working group? We'll do that one first. So I put in this is the total sums of squares from that previous model. And here is the full model sums of squares. This is the number that I needed to get that I don't have. And the way that I got it is to fit a reduced model. For instance, leaving out the 2 effects of age. If I leave out age, my model sums of squares is only this. So then I can compute the difference. The model that has age in it, those sums of squares, minus the model that doesn't have age in it, divided by the total. And so that gives me this number, 0.08, which is telling me how much of the model R square is due to age. That's what's known as the semi-partial correlation squared. So go back to the main result here. So 29% of the variance is what all 7 slopes captured simultaneously. What I just found out is that, where's age? Who's doing age? So 29%, 8% of that was due to age. So the remaining 21% was due to the other 2 variables. And so I did that for each set in turn. Here's working class, captured 4%, age captured 8%, and education captured another 8%. And the 3 of those do not sum to the original R square because R square also includes the covariances between the variables that none of them gets credit for. So this is a way to sort of piece apart how much of the total R square is due to each of these different pieces. The 3 variables characterized by the 7 slopes lumped together. So just to repeat, you guys don't have to do this on your homework. I'm showing you how, if you want to use Stata to do analyses, you would generate these things. What I'm asking you to do instead is to watch the model R square get higher and higher, and to use the difference in the R square as the effect size directly. So you can do that in hierarchical models, as I'm asking you to do in homework. Okay. So the SAS output then, the extra piece that is given in SAS is what I just had to reverse engineer out of Stata. So SAS has a heading total variation accounted for, and there's a column called semi-partial eta square. So the numbers that I just had to go and get, so 0.2887 is the R square for the overall model. 4% is due to working class, 8% was due to age, and 8% was due to education. And 4, 8, and 8 do not sum to 29 because the model R square also uses the information that is common to the predictors that none of them each gets credit for. And that was the "this is us" analogy. If more than one kid cleaned the same room, we can't give any kid credit for a room that both people cleaned. So this is trying to piece apart the R square to get effect sizes that go with each predictor, but their joint contribution that none of them gets credit for does still show up in the R square. So because SAS readily gives this information to you, but Stata does not, I'm not asking you to generate semi-partial eta squares in your homework, trying to be fair. What I'm asking you to do is to check the change in the model R square as you add things to it, which gives you the exact same information in a way that all of you can get to it. So again, new thing that you have to do, these contrasts, 1 or 2 of them, I believe, and the analog in Stata, these tests. That's the only new thing on homework 5. All right, questions before we wrap up for today?
Is all the information for the FA5 available to us? Like, could we do that right now?
Yes, please do that before the next class. That way we can talk about it.
Perfect. Okay, thank you.
All right, anything else? All right, then thanks for coming. See you Thursday. Let me know if you need anything. Peace out, folks.